In this video, we're going to see how following the Aufbau principle and Hund's rule can actually lead to incorrect electron configurations. And so in other words, we're going to be identifying anomalies in writing electron configurations. Now the most common examples cited are for chromium and copper. Now the actual electron configuration for chromium has the argon core of 18 electrons plus 1 electron in the 4s subshell and 5 electrons in the 3d subshells. So the argon core 4s1, 3d5. Now if we followed the Aufbau principle, we would expect it to be argon core 4s2, 3d4. Similarly with copper, the actual electron configuration has the argon core 4s1, 3d10 instead of argon core 4s2, 3d9, which is what we'd expect if we followed the Aufbau principle. So let's use our orbital diagrams to see if we can get our heads around why this might be the case. And these anomalies occur beyond element number 20. So I'm going to fill up the orbital diagram with 20 electrons there using the Aufbau principle and Hund's rule. And we've actually got the orbital diagram for element number 20, which is calcium. So it has the argon core plus the 2 electrons in the 4s subshell there. So there we can see the argon core of electrons, 18 electrons, completely filled shells and subshells there, and we know that argon is quite a stable element. And then we've got the 4s2 electrons to make up electrons number 19 and 20 in calcium there. So according to the Aufbau principle, the next highest subshell that needs to be filled is the 3d subshell. So if we go from element number 20 to number 21, scandium, we can add another electron into that 3d subshell and we get the electron configuration of the argon core 4s2, 3d1. Titanium number 22 has the argon core 4s2, 3d2. Add another electron, we get vanadium, argon core 4s2, 3d3. Add another electron, we get to chromium number 24. Now we would expect it to follow the same pattern and have the argon core 4s2, 3d4, and that's what the orbital diagram is showing. But as you can see here, the electron configuration is actually 4s1, 3d5. And it's as if one of these electrons here actually prefers to sit over here in this d subshell to fill in that 5th orbital there, so that we've got a half-filled subshell. And it turns out that half-filled subshells have stability associated with them, so that the argon core with 4s1, 3d5 is actually more stable than the argon core 4s2, 3d4. And so what we've got is a situation now where the orbital diagram with that s electron moving over into the d subshell actually now matches the electron configuration shown on the right hand side there. So if we wanted to continue to add electrons in, we would get to element number 25, and we're going to fill in the lowest available orbital in terms of its energy, and that is still the 4s orbital. So the 25th electron would actually go into that 4s subshell there, and we've got the manganese electron configuration of having the argon core 4s2, 3d5, and so we're back on track as to what we would expect. Start filling up the 3d subshell again, so we get to element 26, add another electron there. We've got the argon core 4s2, 3d6. Cobalt number 27, the argon core 4s2, 3d7. We get to nickel number 28, the argon core 4s2, 3d8. When we get to copper number 29, we see that the orbital diagram is showing that we've got the argon core 4s2, 3d9, but the actual electron configuration that's most stable is the argon core 4s1, 3d10. And again, it's as if one of these electrons in the 4s subshell actually prefers to be over in the 3d subshell now, this time to complete a full subshell. And again, it turns out that filled subshells have an inherent stability about them, so that the electron configuration of having an argon core 4s1 3d10 is actually more stable than the argon core 4s2 3d9, which would be the one that we would predict. So we can go on and add a 30th electron, and we would need to fill in the lowest available energy orbital, which would be the 4s2. So we stick that 30th electron into that subshell there, and we've got the zinc electron configuration of being the argon core 4s2 3d10. So we're back on track as far as what we would expect. So filled shells and half-filled shells have an inherent stability, and they are therefore responsible for these anomalous electron configurations that we see for chromium and copper. Now there are other examples, silver, gold, palladium and molybdenum, to add to the copper and chrome examples, and again we can see that the actual electron configuration deviates from what we would predict due to the fact that we want to get half-filled D subshells there or completely filled D subshells.